Okay, so the purpose of my talk is I'm going to be just giving a brief overview of things that need to be looked at when you're trying to decipher whether or not there was a flash flood or a debris flow below or within a recently burned watershed. It's not a simple task to do. So I don't want anyone to be under the illusion that you're going to walk out of here and be able to figure this out the very first time you go out in the field. It's one of those things that it's sort of a continuum between a flood and a debris flow. And the flow can actually evolve at the exact same location in time. So what may start out as a debris flow may become a flood and eradicate any evidence of the earlier debris flow. Or you could have a perfectly preserved debris flow that's really easy to identify. But that's a fairly rare occurrence. So the idea here is just to kind of give you an idea of things that we look for in the field and some examples of what these things might look like, so that we can go forward and then think about verification and how we can use some help getting data and input into our models so we can make them better. And then Francis will give an overview of sort of what the data requirements are and how we might use those. So just some key points that I hope you take home from this presentation is that flash floods and debris flows may look pretty similar in the field after an event, but it's the behavior of these flows and the differences in the behavior that are really important from trying to figure out where they're going to occur, when they're going to occur, and how big they're going to be, and how hazardous they're going to be. So while the homeowner that gets a rock in their house, it may largely be an academic distinction for them, whether or not it was a flash flood or a debris flow, from trying to forecast these things and predict these things, it really does matter to us at the scientific level. The second key point is that we make predictions of where and when debris flows are going to occur and how big they're going to be, and that's great, but we really want to do a better job. So we need to evaluate our model predictions for accuracy in a variety of settings. Currently, we have a lot of data from the semi-arid Intermountain West in Southern California, but there's a lot of places where we haven't worked yet, such as Northern California and maybe the Pacific Northwest, where debris flows are an issue, but we don't have data in our empirical database from these environments. So being able to work with you guys and get more observations will be great and allow us to make better predictions in different places. Let's see, verification. It requires consistency in the rainfall measurements and response observations. So we want to make sure that we're on the same page, that we're able to have confidence in those observations that are going into the database, as you know, it's the whole garbage in, garbage out thing. So we want to make sure that we're all on the same page and putting in good information. And then finally, it's all about quality of observations and not quantity. And Francis is going to touch on this too, but I would rather have 2 really good observations that we're confident in than 20 that we don't really know, that we're not really confident in. The more people out there, the better chance we have of getting these quality observations. So let's just kind of give an overview of, and some of you have probably seen these slides before in the WebExes that I've given, just sort of the different flavors of landslides and debris flows, and then we'll kind of focus in on what happens post-fire. So at sort of one end of the continuum of landslides and debris flows is maybe the Oso landslide from 2014, March of 2014. This is sort of a deep-seated failure where an entire hill slope gave way. That material that broke off from the hill slope flowed downhill and devastated the community that was at the toe of the slope, unfortunately resulting in the 43 fatalities. So this is sort of one end of the continuum, and this is what people often think of when they think of landslides and debris flows, are these big, giant, discrete failures that are, you know, tens of meters deep. Sort of moving closer towards post-fire debris flows are shallow landslides, and shallow landslides that generate debris flows. So what happens here is you'll get prolonged rainfall over a period of a few days, perhaps. The amount of water within the soil column builds up over that storm period. Eventually, some critical threshold is reached, and the slope fails. Typically, these are 10 meters-ish wide or less by a handful of meters deep. The material that fails from the hill slope then mobilizes as a debris flow as it moves down slope, and can impact the community or infrastructure at the base of the slide and the flow. In this case, this is an event, a pretty famous one from the Bay Area, Pacifica, California, in January of 1982, and unfortunately resulted in the 3 fatalities, all children, as they were sleeping in their home. Now, when you look at post-fire debris flows, they're a little bit different animal in terms of how they get started. You don't see those discrete scars at the top of them. This is a photo that was taken by one of our colleagues in Santa Cruz of the surface after the January 2018 debris flows in Montecito. So instead of a discrete failure in a landslide scar, what you have is progressive entrainment of material. And what happens here is that the rain falls harder than the ground can absorb, so you get runoff. That runoff moves down slope from the top of the hill towards the bottom of the hill, and as it moves down slope, it picks up more and more material, and then there's some transition from just sediment-laden overland flow to a debris flow, typically somewhere on the hill slope or as it reaches the gully or within the channel itself. So you don't have that discrete source of material. Instead, you have material that's coming from all over the place, and that picks up speed and momentum and mass as it moves in the downslope direction. Another view of what the channel system looked like above Montecito. Again, there are probably a couple shallow landslides you could pick out in there, but the primary triggering mechanism for those types of debris flows was that progressive sediment entrainment. So erosion and runoff, and then a coalescence of material as you move down slope. So what do debris flows look like when they finally make it out? This video is from, I believe it's Pakistan. I'm not sure the exact time or date. And this also is in a burn area, but it's a very good example of what a debris flow looks like. I realize it's probably a bit slow and choppy for you, but hopefully you can get the general gist of what's going on. So here's the initial surge of the debris flow. You have a bunch of boulders that pile up in the front of it, so you get this segregation of grains where the largest material is near the front, and there's a big surge of material, lots of boulders, all kind of floating on top of one another. And you can see how this could be pretty destructive, and you would not want to be situated downstream. If you can see the video now, there's a bit more of a watery tail to that flow, so the actual height of the flow itself is probably a little bit less. The water content is much higher. So this is a pretty textbook example of what a debris flow might look like. Here you have the flow locking up, and then you see just the water running out from the base of the flow. So while the evidence upstream may be of a debris flow, if you're 200 meters or so downstream, you might only see a flood because the debris flow only traveled to where it entered the main stem of the channel. So this is a pretty classic example of what a debris flow looks like, even though it's not from a burn area. We've got video from one of our monitoring sites in Southern California. This is the 2016 fish fire, and the debris flow was on January 20th of 2017. This is a pretty small watershed. The overall size is maybe a few football fields wide by a few more high, and the rainfall intensity was about 30 millimeters an hour, and this is a burn area. So you get this immediate surge of flow once the intensity of the rain kicks up. It's pretty watery at this point, but we'll start seeing some more material coming through. More watery than the last video I showed, but here's a good chunk of debris flow coming through now. Lots of clasts that are kind of supported by one another. The watery recessional flow here, well, it's not recessional because it's getting bigger. But lots of stuff mixed in, really big boulders, lots of mud, and pretty destructive, and something you would not want to be standing in the channel of or in the immediate vicinity of the channel. And then finally, at some point here, it ramps up again, and we get some Indiana Jones boulders rolling through in sort of the waterier flow towards the end of the debris flow surge. So that's pretty typical of what you see in a recently burned area. A little bit more watery than the flow from Pakistan, but again, clearly a debris flow and not a flood. Let's see, we've got another guy here. I don't know if I'm going to be able to make this work, but I'll give it my best shot. Let's see, let me get that one up. And so we can highlight the difference between that and what you might see in a flash flood. Now again, this isn't a burn area, but it's pretty similar to what a flood you would see in a burn area. Do you see a YouTube video right now? Somebody confirm that?
Yeah.
Okay, good. So lots of woody debris at the front of it. It's transporting a lot of things. It's probably moving a bit faster than you could run, so you wouldn't want to be in the way of this. You can see that it's carrying plenty of material. Could be potentially destructive for any infrastructure downstream. It would certainly carry cars or people away if you were caught in this flow. It could definitely result in damage to homes, infrastructure, and fatalities for anybody in the way. But you can see it doesn't quite have the dynamics of a debris flow. It doesn't have the clasts being supported, the big rocks embedded in the flow on top, like the video from Pakistan or our camera in Las Lomas. So yeah, this is a pretty classic flood, and something that, while it's not a burn area, would be similar to what you would see below a burn area during a flood event. Let's move on now. And another flood, this time from the Rim Fire, 2013 fire in just near Yosemite in California. This is a pretty short video, but yeah, it's quite watery. It doesn't have a lot of material in it. You certainly wouldn't want to be standing in the channel, but it does not have the dynamics of a debris flow like we saw in the other two debris flow videos. Here's an example from the Waldo Canyon fire, which occurred in 2012 just outside of Colorado Springs, Colorado. This storm, I believe, was in July of 2013, so the following summer. This part of it is probably mostly flood, but there was a debris flow up high. So again, like I highlighted with the Pakistan video, where you may have evidence of flooding downstream, if you go high enough in the upstream direction, there could be evidence of debris flow. So you have to consider, the full longitudinal profile of that watershed when you want to make a determination of whether or not there was a debris flow somewhere in that watershed. You can't just look at the bottom end. This is a pretty intense but short storm. I think the rainfall intensities were somewhere around 35 millimeters an hour, or a little over an inch an hour. But the storm only lasted about 15 minutes and caused all kinds of problems downstream in Manitou Springs. And there was a fatality associated with the flooding down in Colorado Springs. But again, very short storm, lots of destruction, but this is definitely a flood and not a debris flow. In the video that's being shown now, there was a debris flow up high. So, like I said before, to the homeowner, it doesn't really matter if that boulder got transported by a flood or a debris flow. There's a boulder in their living room and they're not happy about it. But from a scientific perspective, it does matter. And my colleague Jason Keene wrote a really nice paper about why that difference matters. So if you were to take the exact same watershed and dump the exact same amount of rainfall in it, in the exact same rainfall intensity, if you have a debris flow, it's going to be worse than a flood. So here's why. The height of a debris flow, or the maximum stage of that debris flow, for the exact same amount of water going into the system can be up to 5 times greater for a debris flow than it is for a flood. So it has a higher potential for damaging bridges and infrastructure, has a higher potential for exceeding the banks of the stream channel, which could cause it to overtop the channel and go in other places where normal water wouldn't flow. And it has a much higher potential for destruction. The mass and the momentum of these flows is quite a bit higher. If we compare velocities between floods and debris flows, it can be quite a bit greater for a debris flow. There's no real fixed number. It sort of depends on channel gradient, the fluid content of the debris flow itself, and a few other factors that are going to determine how fast that flow is going. But let's just say if it's the same speed, but it's a much higher debris flow and a lot more mass, then the debris flow is obviously going to be much more destructive than the flash flood. So we're concerned about the debris flows and how they initiate because they're different in initiation than the floods are, but also the impact of these events is much different. So that's why in the Landslide Hazards program, we focus largely on debris flows. So the key points here for these last few slides are that flash floods and debris flows might look similar, but debris flows are more destructive. There's a whole bunch of different flavors of debris flows, from those being generated by big, massive failures to the runoff-generated things that we see in recently burned areas. And those that occur in the burn areas are closest in relationship to the floods, just because of its very similar triggering mechanisms, but they're definitely a different animal than a flash flood. And then finally, as we saw in the Waldo Canyon video, you can get floods and debris flows within the same event. So it may start off as a debris flow and evolve into a flood. It may start off as a flood and have periods of debris flow. So it's difficult to untangle those in a lot of instances, especially in burn areas. But fortunately, the debris flows leave some fairly distinct features on the landscape that hopefully will be preserved after an event that we can go out and look and find in the field and say, oh, yes, this was a debris flow, or we don't see any evidence of debris flow, so it probably was just a flood event. And just sort of at the most basic level is that floods and debris flows both produce fans. Alluvial fans just develop over time with multiple flood or debris flow events. There's this aggradation of material at the base of the mountain front, which grows into a fan shape over time and with repeated events. Debris flow fans and flood and alluvial fans or fans that are made by floods, they have different morphometry. They have different shapes and features on them, but they both make these fan shapes. So we're not going to get too much into the broader scale fan morphometry today. Instead, we're going to zoom in a little bit more. But here we've got a nice example of fan debris flow impacting a fan in Southern California in a burn area. This is in the station fire of 2009. You can see that there was a debris flow coming down from sort of a side drainage onto the fan and caused deposition on the fan itself, as well as sort of the main channel. You get some debris flow deposition there as well. And with repeated fires, repeated intense storms, and repeated debris flows, these fans build up over a period of time. So you can go out even in places that haven't burned in a while and say, hey, there's fans here, and we probably should be concerned about flooding and debris flow in these locations because they have produced these types of events in the past. Of course, Montecito is built almost entirely on a fan. So there was some advance notice that this type of event would be possible. There were flows in the 60s, 70s, and early mid-90s, floods and debris flows that impacted the town. If you were to walk around Montecito, there's a lot of places where you see really big boulders pretty far from the mountain front. And in some cases, you kind of have to wonder how they got there. And so the area of Montecito is built on a fan. Lots of communities in the western U.S. are built on fans. So it's really important that we recognize these features at a broader scale so we can define these areas as being potentially hazardous if there is a fire or a long, prolonged rainfall or intense rainfall up above these areas. If we zoom in a little bit, this is an alpine debris fan, so not a burn area, but it has the photo does a really good job of highlighting some of the features that you can find that are associated with debris flows on the fan itself. So we have these features that are known as levees. These are these kind of linear features that the line extends from upslope to downslope. So it's parallel to the flow direction. And this is caused as the debris flow comes down, it kind of pushes material off to the side and deposits these rocks there. You get these nice U-shaped channels that are evident on debris flow fans. And then finally, if the debris flow comes down, but it doesn't quite make it out to the main stem or the main channel and get swept away by water flow, you get these terminal lobes, and it's basically just a bunch of material that piles up where the debris flow stops. So this is a pretty classic example of what you would see in a perfect world on a fan. Of course, we don't live in a perfect world, but a lot of times we do get perfect debris flows even in an imperfect world. And this is one I didn't go to this, but Francis documented this one really well. This is in central Washington. It's sort of a mystery debris flow because the rainfall intensity is pretty low, but it was a debris flow generated by runoff. And there's a few distinct features you see. You get your levees off to on the sides of the flow, the channel itself, where the material is pushed off to the side. And you get this nice U-shaped channel that forms from a nice debris flow. So this is a pretty classic example of what you would see in a debris flow channel in a recently burned area. Typically, they're not quite this nice, though, but this is a really, really good example. If you go down to further down in the watershed, you might get some really nice levees that are formed on the side of the channel. So again, you get this pile of boulders. If you look off to the upper right-hand corner of the image, you can see that's where the stream channel was. So a big debris flow came through here, deposited all these materials, and these are pretty easy to see in the field. And again, another very, very classic example of what a levee might look like. There's a pickaxe for scale, so we're looking at boulders, maybe a meter or so in diameter. So a good size event, definitely hazardous. Again, we'll take a look at another channel that's been impacted by a debris flow. We've got a nice U-shaped channel. We've got our levees that have formed with a hat for scale, so maybe 25 centimeters or so, or a foot or two. Boulders of rocks a foot or two in diameter. But pretty classic, well-preserved evidence of a debris flow. So if we think about these features and structures, the debris flows imprint a distinct signature upon the landscape at a variety of spatial scales. So everything from a big fan all the way down to looking at the smaller scale features such as levees, lobes, and U-shaped channels. We can look at things from the air and satellite and identify fans and oftentimes identify these features. So bigger levees will pop out sometimes in aerial photography or LiDAR data. But the fans certainly are something we can see in the field and identify. We can see in the imagery and be able to say, hey, this is a hazardous place that we need to be concerned about. And it also can guide us to, during verification efforts, to find places to go look for debris flows or floods. It's a good idea to look for places that have already produced these types of events in the past. But as we can see, and we'll see in the next couple slides, is that aerial photography and LiDAR are great, and remote sensing are great, but nothing beats boots on the ground for identifying debris flow features. Oftentimes the debris flow flows downstream out of the burned area, and so you won't be able to see that in an aerial photography. The LiDAR may not be of sufficient quality to really be able to see some of these smaller features that are imprinted up on the landscape. So we really rely upon getting out into the field and making observations and taking pictures and collecting GPS locations of where you're making your observation, because that really truly is the best way to figure out if it was a debris flow or not. So once you get out, and now that we've established that it's best to get out in the field, once you're out in the field, there's a few things you need to look for. And this is where we're going to jump into the science weeds for a little bit here. But I'm going to try to keep it as simple as possible. So there's sort of three basic things that you want to look for when you're looking at deposits and trying to figure out if they're a flood or a debris flow. The first is the degree of sorting. And that just basically describes the distribution of grain sizes. So if you have a whole bunch of different grain sizes all mixed up, so you have big boulders and tiny little pebbles and mud all mixed up, you would consider that unsorted. If you have a whole bunch of rocks that are about the same size, pebbles or cobbles, then that's going to be well sorted if they're pretty much all the same size. So that's sorting. Stratification, I'll have some pictures highlighting these as well, but I just want to get you familiar with the terminology. The second is stratification. This describes the layered appearance of different grain sizes. So if they're layered, they're stratified. If there's no layering, they're unstratified. And then finally, you want to look at how rocks are kind of related to one another and what's in between them. So if you pick up a rock, you look and see, is it another rock underneath, or is there mud in between the rocks? If it's supported by a rock, that's classed supported. If it's supported by mud mixed in between the other rocks, well, that's matrix supported. And so a matrix support is a pretty clear indication of a debris flow and not a flood. So here's a picture of some sediments that were deposited during a debris flow in 2007 in San Diego County. If we look, we can see that there's a bunch of rocks of different sizes, so it's not very well sorted. You don't really see any layering in this deposit, so we would consider that non-stratified. And if you were to pick up any one of those rocks, it would be almost completely supported by mud between that and the other rocks. So we would consider that matrix supported. So this is a pretty clear picture and a pretty textbook example of a debris flow deposit. It's unsorted, it's non-stratified, and it's matrix supported. We've got an example from Washington. This time Jeff Coe and Francis trenched a fan in central Washington and found debris flows, historic debris flows. So this is an older deposit, but you can see, again, you don't see sorting. You've got a variety of different particle sizes in there. You don't really have any layering. Any sort of linear features you see is largely the root system from different surfaces over time. And if you were to take those rocks out and look at what's holding them up, it would be a muddy matrix, and it would not be classed. So again, this is a pretty typical debris flow deposit. Unsorted, non-stratified, and matrix supported. A lot of times it's not quite as easy as that, and you've got to find really small examples of what happened in the past, because the watery flood flow at the end of the event may have eradicated the evidence of what happened at the beginning. So sometimes you got to look around corners and look in protected areas. And this is a debris flow deposit. It's a levee, and if you were to pick up those rocks, you would see that they're matrix supported. So you know your feature, you know it's a levee, and then you know from the matrix support of those boulders that it was a debris flow. Getting over towards flood deposits, they look quite a bit different. And so you can make these determinations in the field, but you have to make a lot of observations for the same location to really be able to figure it out. So here we've got a pretty classic example of a flood deposit. You can see that a lot of the rocks that are the same size are kind of grouped together. You've got a group right in the middle of the image of similar size. I'd call them either gravel or cobble. I'm not quite sure the scale on this, so there's a lens cap for scale. So gravel, cobble-sized rocks all grouped together. And then you've got some fine material both above and below that. So the fine material got grouped together. So we're going to call that pretty well sorted. You can see distinct layers within that deposit, so we're going to call that stratified. And then if you were to pick up those rocks that are on the top there, you would see that there's no mud in between. So those are what we consider class supported, because it's just other rocks supporting the rocks in the deposit. So a pretty classic flood deposit, well sorted, stratified, and class supported. This one's a little bit trickier. So what we don't see as well, but we still see it if we kind of squint our eyes a little bit, is that it's moderately sorted. So there are groups of rocks that are kind of together that are about the same particle size. It's somewhat stratified. Again, there's a few layers in there of similar size material, and it is class supported in that rocks are just supporting other rocks, and there's not the big muddy matrix that you would see in the debris flow. But again, this is a little trickier. It's not quite as clear evidence, but it was determined that this was a flood deposit. And then finally, you can zoom out a little bit, and sometimes that helps too. This was, I believe, a outburst flood in New Zealand after the earthquake in 2016. There's a landslide that dammed a river. The water built up behind the landslide and burst catastrophically and caused a flood. And you can see some stratified deposits along the bottom left corner of the image. And then if you were to go in there and take a look, the class would be supporting one another where there's coarse material. So the key points here is that debris flow deposits tend to be unsorted, unstratified, matrix supported, and then I didn't get into massive and imbricated because we didn't have time. Flood deposits tend to be sorted, stratified, and class supported. And again, it's really best to get out on the ground and try to figure out what's going on if it was a flood or a debris flow, because it's really hard to do from pictures alone. So the challenge of doing this, though, is that oftentimes you'll have floods and debris flows occurring at the same location or even within the same event. So here you have a nice perfect debris flow deposit on top of a perfect flood deposit. And I think this was in the same event. So it's in the same location, in the same event, you can have both floods and debris flows. So at the top is our debris flow deposit. Oh, sorry, I should say flood deposit at the bottom. And again, the flood can eradicate any evidence of flow. So if you're walking upstream and you see this tangled nest on the left, you might not think much of it. But if you walk around to the other side and take a look where the flow might have been a bit protected or deflected from the trees, you can see pretty clear evidence that this was a debris flow. You've got unsorted boulders that are piled up and they're matrix supported. Kind of a closer up image of what that looks like with a nice debris flow deposit tucked up behind a tree. So another challenge is that the videos might be a bit ambiguous. So if we go to our Palm Springs video, I think most of you have probably seen this from just a couple weeks ago. My initial hunch is that this was a debris flow, but from the video evidence itself, you can't really make that determination just from video. My hunch is that it was a debris flow. If we got out in the field, I would assume that we would see some evidence of boulder levees or other features, deposits that are clearly debris flow, but we just can't make that determination from the video alone. We really need to get out in the field and see what that thing looked like. So I think, so just wrapping up, debris flows and floods can occur within the same flow event. The recessional flood flow can eradicate evidence of an earlier debris flow. And finally, once again, nothing beats boots on the ground for identifying the differences between debris flow and flood deposits.